So, well, first of all, thank you for your kind invitation to talk in this workshop. Today, I'm going to talk about some recent advances in machine learning for vegetation monitoring. I'm in a lab in Valencia, in the University of Valencia, called Image Processing Laboratory, and we are working towards developing new algorithms for different applications in the Earth system science. And I will show you some methodologies that we have been developing in the last years to tackle this really challenging and pressing problems of vegetation monitoring from space. So, well, first of all, what is machine learning? Well, this is machine learning in a nutshell. So essentially, most of the times you have data, X, and you want to create a function f that basically approximates another target variable y. But maybe sometimes you don't have this y, right? So you don't have observational data that you want to approximate. So you only have to extract features from X that are good proxies to approximate whatever target variable that you want to. Traditionally, the main difference between machine learning and other parametric or non-parametric modeling is that this function f, is is a non-parametric, non-linear function, and most importantly, this is learned from data. So in principle, you should have access to these pairs of data, X and Y, that you can learn from. So let me show you just a couple of examples on how typically these machine learning models have been used for vegetation parameter estimation. For example, you can go to the field and get through a terrestrial campaign some observations and variables and in situ measurements. For example, here in a nearby region here in Valencia, we were measuring in situ leaf level chlorophyll content on leaf area index. And then at the same time that the terrestrial campaign is happening, we had CRIS sensor images that had the spectral imagery. So in the end, you just collocate this data, and after atmospheric and geometric corrections, you have your beautiful database that you can learn from. In here, we just develop a bunch of methods. In particular, one that it is actually working very well is Gaussian processes. Not only because once that you have trained with these X and Y pairs, you can, of course, do predictions for the unseen data, and you can generate like chlorophyll content or leaf area index or vegetation cover of upper estimates, spatially explicit, also temporally well resolved. But the Gaussian processes also allows you to estimate uncertainty in your point-wise estimate. So you can not only get the top row figures with the estimates, but also the uncertainty estimates associated to each one of them. And you can, for example, start like thinking about confidence on the predictions, masking unreliable estimates, or even just trying to account for anomalies in your data acquisition process, for example. Well, maybe, and this has been already treated in this workshop, but maybe you want to go global, and for that, instead of going just with a regional campaign, you can go global and exploit information acquired by the flux network sensors. So, well, you have a good bunch of tower measurements here, accounting for CO2 energy and heat fluxes that you can get some estimates, and then together with together with the MODIS observations that this has been also mentioned before, you can actually do this regression exercise. So you can extract some reasonable features out of X, out of the MODIS sensor, plus some ancillary meteorological variables, for example. So you derive, let's say, leaf area index, CBI, and DBI, land surface temperature, a good bunch of features. And these serve the purpose of creating your machine learning model to estimate the GPP measured or estimated at a flux tower level. Then this allows you to estimate different parameters. Here we were interested in GPP, but also energy and heat fluxes. And that allows us to, to start doing science with that. So you can plot here, for example, in these 3D color map, you have the latent energy, the heat energy, and also the the radiation. So you can start identifying anomalies in space and time, hotspots, etc. No? So these are like two standard examples of what people have been doing for several years already when it comes to spatialize some parameters of interest. But what happens is that typically one wants to go deeper and with finer spatial and temporally resolved data. So you want to go with higher spatial resolution, with higher, in principle, sub-daily temporal resolutions, and that involves not only the lack of data for training the models, but also the lack of computational resources. But this can be treated with in this Google Cloud, in the Google Earth Engine, where you basically can upscale to globally and at a finer spatial and temporal resolutions, these problems, right? So I will show you just a couple of examples here. The beauty or the advantages of Google Earth Engine, that it is essentially a platform where you don't have to worry too much about the data pre-processing, but all the data is there, and you only have to, focus on the model development. I'm going to show you a couple of examples that we have been working on the last decade. So the first one is what happens if you don't have in situ measurements. So, well, maybe you have to rely on models, and in this case, we are relying on an RTM, on a rapid transfer model called ProSail. And well, you parameterize it, you generate this lookup table of parameters and reflectance data, and then you can run your favorite machine learning model to invert back, and from reflectance data, you can estimate these parameters. In this particular case, we were generating liver index, FAPAR, and canopy water content by inverting this ProSail with a set of with a generated lookup table from ProSail, right? So this is one thing that we can do. Another potentially useful maps and products that we have developed in the last years is about a full methodology to derive global maps of leap traits using both remote sensing and climatic data, and also making use of different spatial resolutions provided by MODIS, but also we want to exploit the potential of Landsat at a finer spatial resolution to estimate better the abundances of PFTs in a particular MODIS pixel size. So the full model, it is capable to exploit observational data acquired in a database of traits called TRI, and then the exercise is pretty much the same. It's a regression problem where you depart from MODIS reflectance data and some ancillary climatic data as well at 500 meters spatial resolution, and then you derive these global trait maps again at 500 meters. So we run different algorithms here: random forest, of course, linear regression, Gaussian processes, neural networks, and then these methods can be trained offline and then implemented online in the Google Earth Engine, so you can generate these maps pretty fast as well, right? A third methodology that I would like to introduce today is what happens if you want to generate very high spatial resolution parameters, but also continuously in time, and also with uncertainties, well-calibrated uncertainties. Well, this is a work that we just published this year. In this particular work, we are using, you see here, two boxes, essentially. These yellow boxes stand for algorithms or models. Essentially, you have this high star FM algorithm that basically blends Landsat and MODIS data in a sort of unbiased Kalman filtering approach, very similar to what you guys have presented before with the data simulation strategies. In this case, the high star FM is taking this reflectance data, and it is providing you like harmonized data, gap field data. So you have a continuous in space and time reflectances, and also associated uncertainties. And this is a key issue here in the whole pipeline, because we will use both the reflectance data that will be used in our second step, the neural network, that it has been trained as before, trained to invert a particular lookup table derived from ProSail. But again, we are not only here interested in providing biophysical parameters. In this case, we are providing those estimates at 30 meters resolution, so at Landsat resolution. This is because the high-star FM has provided us with this very fine-grained spatial resolution. But we are also interested in providing a total uncertainty, a more realistic uncertainty, I would say. And what is a total uncertainty? Well, the uncertainty has two particular counterparts here. So one is the data uncertainty, and the other is the model uncertainty, the neural network uncertainty. So on the one hand side, we have the epsilon reflectances, so the uncertainty in the data generating process. And this data is used by the neural network. So it is propagated through this model. And we can estimate the variance or the uncertainty propagated through the neural network, just basically looking at the Jacobian of the neural network and propagating this uncertainty. This is quite easy. The other problem, the other uncertainty term comes from the neural network itself, from the model uncertainty. Right? So for that, we use a method called Monte Carlo dropout, MC dropout, that it is able to estimate these sigma E, the uncertainty associated to the model inaccuracies. Okay, we can assume that both are independent, so we can sum them up, and we do. But now there is a second step, which is the calibration. We need to calibrate these uncertainties. I'm not going to enter into the detail how this is done, but essentially after the whole story, you end up with a total uncertainty, not only the counterparts, the different pieces of the uncertainty, and of course the biophysical parameters are 30 meters. So we can go continental, also continuous in time, and you can generate not only the prediction for different parameters, life, upper, and FVC, but also these pieces of information uncertainty, right? The epistemic, the aleatoric uncertainty, and the total uncertainty. And you can see that the patterns, the spatial patterns, are quite different. And this is basically due to the different characteristics of the terrain, for the different importance of the errors committed by the model, or the data and reliability on the fusion process, and also, of course, because the different quantities are going to affect differently in the estimation of the particular biophysical parameter. And we can go with not only standard biophysical parameters, but also, again, to provide very high spatial resolution fluxes. Like in this case, we are providing GPP at very fine-grained scale of 30 meters, and you can start doing science with that. What is interesting here is that the patterns, even though that we are working at a pixel level at this 30 meter spatial resolution, we can derive like plausible maps. I mean, the maps look quite smooth. The temporal variability has been assessed and contrasted with in situ measurements and estimates. So you can see clearly high spatial details, and also at a continental, very broad scale, right? So every single pixel here is 30 meters. So you can go and do your applications at these very continuous, homogeneous, at scale products. And the good thing of it is that it is implemented in a Google Earth engine, so everything is computationally and quite memory efficient. But now, in these days, we are finding that machine learning cannot solve everything. Machine learning can solve a lot of things, but still, it struggles in problems when you have a very high dimensional problems and very few data to train or to learn from. In these cases, also in the cases that you want to extrapolate or to say something about the uncertainty in unseen regions, machine learning struggles. And there is this new field, let's say, where one wants to interact with domain experts, domain knowledge, and a priori functions in such a way that you modify your function of interest, this F machine, not only using or exploiting the patterns in X, but also incorporating this domain knowledge or differential equations in the form of differential equations or priors to the model, right? So this is the field called physics-aware machine learning. I will show you just 3 examples. There are many, but I'm going to show you 3 particular and distinct examples of what physics and machine learning interact each other. So the first one is the obvious one, and probably you already have heard about this, surrogate modeling or emulation, right? So very often we are using very complex, computationally very complex codes like radiative transfer models or subcomponents of a climate model, and you are not able to run these models for a long time or for many years or for many different instances, no? They are costly. So one way that one can interact with machine learning is just basically to launch as many simulations as you can, and then try to mimic this relationship of input-output relations, parameters, reflectances, for example, with machine learning. So once that the machine learning model is trained, it is very fast at the testing time, right? At deployment time. So this is one of the advantages, and it has been advocated most of the times for the sake of speed only. But there are other things, other advantages that one can actually exploit from this exercise of emulation. The second thing is that one can derive automatic sensitivity analysis from machine learning models, because now we have tools to do exact derivatives of the non-linear, non-parametric, very complicated functions. So this is good because you can actually look at what are the parameters and what the models have learned, and you can assess if they have captured any physics or not. In this case, you can see here in the middle picture, the sensitivity analysis provided by different models. By our Gaussian process here, wait a second here, you have also our kernel regression and also neural network. And on the left top corner, you have here the true sensitivity analysis derived from the lookup table, right? So, well, apparently they have captured some physics out of this exercise, right? So you can roughly trust that, no? And in terms of accuracy and speed, you can say that the methods are performing pretty well. In our experience, again, Gaussian processes perform best among the others. And it is not only because of the error. You can see the picture on the left. The error is much slower for the orange curve here, independently of the wavelength. Not only also because of the computational efficiency, but also because it provides, again, confidence intervals for the prediction. So you can start using these products, not only the emulation exercise, but also uncertainty for the spectral bands, right? So that's a good advantage, no? And you can reuse and you can use these GPs in further processing. Okay, so this is just one interaction between machine learning and models. The second one is how to blend observations and simulations. Again, here we use a Gaussian process for doing this. In this particular case, you can see on the left-hand side a very simple toy example that you are trying to learn this curve from this observational data in blue dots, right? So in the in-sample region in the middle between -0.5 and 0.5, whatever model you use will do it right, because you have enough representativity and you will fit this curve very, very, very well. But what happens when you go outside the region that you are training your model with? Well, what happens is that in the outsample region, models tend to return to the prior. So in this case, it was a zero mean GP prior. So it will tend to provide zero prediction equal to 0. And if they're uncertain, a Gaussian process will tell you, okay, I haven't seen anything like this before, so the uncertainty will increase a lot, right? So this is what you see in dark gray. The uncertainty bars will increase in the outsample region. In our model, this joint Gaussian process, we find a way to combine both observations and simulations. And this way you can perform well in both sides, in the in-sample and in the outsample region. We tried this in, toy examples, but also, of course, in real remote sensing problems. In this case, we were interested in estimating leaf array index from a bunch of simulated data provided by Prusale, plus some in situ measurements. You can see here in the figure bottom right, different sites. And you can see here summarized in the x-axis the reflectance data in terms of NDVI only, and the leaf array index, the parameter that we want to estimate, on the y-axis for different campaigns. And you can see in blue the simulated data. How do they distribute it? So you can really see that the simulated data is covering the whole range, while the real observational data, depending on the vegetation condition, etc., is occupying just a subspace, right? So this is the beauty of the method. It can exploit the two different pieces of information and provide good estimates in the in-sample, but also in the out-sample region, because it can actually fuse the two functions or the two data well. Well, that's the second way. Blend data, right? Of course, you could argue, okay, maybe I can just stack everything together and run my favorite machine learning model. Yes, you could, but it is not that accurate as this one. And the uncertainty is not really well calibrated. Well, and I would like just to finish the presentation with the third field. What we find really exciting these days, we call it hybrid machine learning. And in these particular papers, we have been advocating for the use of combination of machine learning and domain knowledge and process understanding, and in many different ways. I will show you just one. In this particular instantiation, again, it's a Gaussian process. And here we were interested in estimating soil moisture from different sensors. You can see here on the bottom right, SMOS, ASCAT, UMSAT2, and we are here just for the sake of simplicity, we are using time as input variable, only time, right? So it is just basically estimating soil moisture from time, so it is curve fitting, right? But you have a lot of, missing data, uncertainties, different sensors, and you want to do a unique model that it is good for all the models, for all the data sources, for all the sensors simultaneously. There are gaps in different places. And for example, in the case of UMSAT2, because of obvious reasons, the sensor was not existent before June 2012, you don't have data, right? But the model is able to extrapolate across sensors and also, of course, work with missing gaps, with missing measurements in different instances. Well, you can see this structure. It resembles a neural network, but it is not a neural network. It's a Gaussian process. So look, the structure of the model on the left, basically it is multi-output because you are interested in estimating the SMOS, ASCAT, UMSAT2 estimates of soil moisture. Before that, you have H1, H2, HQ. These are filters. I will come back to the definition of what a filter is in a second. But before that, the inputs are functions of time. We call these latent forces. And these latent forces are modeled as Gaussian processes again. These Gaussian processes are combined linearly and then are passed through filters. These filters are actually the key point here. So if you know something about the system that you are trying to model, in this case, soil moisture, you should derive the appropriate filter to account for these relationships. In our case, this filter was derived from a very simple, very naive way of modeling the water balance here. So we assume that there is a first-order ODE relating soil moisture and precipitation, okay? So you parameterize this with an ODE, and then you can derive the corresponding filter. So you derive the equation, and since everything is a Gaussian process, the noise is also Gaussian, and there are linear combinations, the whole thing, the whole model is a Gaussian process again. So it only reduces to a matrix inversion in the end. So what happened? Well, what happened is that the model can actually not only interpolate quite well, but extrapolate across sensors. That's good. And that was kind of expected. But what it was more surprising is when you see on the left-hand side, you see that we took a look at the latent forces. And the latent forces, basically the first one is the pink one here. It resembles quite a lot to the in situ precipitation, but note that this model never saw precipitation, never. So what it is actually learning is that there is some latent force here that can be associated to some process related to precipitation. Since our model specification is not complete because we did not consider evapotranspiration or runoff, etc. The driving force is not completely precipitation, but it has something like 0.8 correlation with it. So the advantage of this is that you get the time decay constant for free from the model. I mean, you estimate it. You learn these driving forces from data, from soil moisture, so you can say something about precipitation just by looking at how much the soil, how moisture is the soil, right? So you can, in principle, go in the same directions, and some colleagues and CNR are going for deriving precipitation from soil moisture, but in our case, it would be non-parametric and non-linear, okay? So just to conclude very easily, my main take-home message is that machine learning is now quite mature, it is quite accurate, and it advantageously can cope with the spatial and temporal heterogeneous data. The second point I would like to mention is that all models, both physical models and machine learning models, are wrong. All of them, they have assumptions, and they are probably not capturing the true relationships, but they are useful. And what I advocate here is for the combination of both through domain knowledge and process understanding, because that will, in principle, with the hope of getting some advantages. The main advantage is that, of course, extrapolation should be improved. As we have seen, uncertainty estimates will be more realistic. And in principle, we should be able to discover new parameters not well characterized in the literature, understand processes from the data themselves. So thank you very much.
Thank you indeed. So we have time to take a couple of questions. Who want to start? Okay, so I can start. So you mentioned during your talk this concept of epistemic uncertainty. So I can guess what you mean here. For me, epistemic uncertainty is the uncertainty about the representation of the system. But so is it what you mean by epistemic uncertainty, and how do you estimate it? This is something that I didn't understand, but it looks very interesting.
Yes, I can say a few words. Essentially, at least in statistics and in machine learning, we distinguish these two sorts of uncertainty: the epistemic uncertainty and the aleatoric uncertainty. So the aleatoric uncertainty is related to the data uncertainty, while the epistemic is more to the related to the model uncertainty. So essentially, you will find some stochastic process that you observe, let's say the observational data, and you have also some uncertainty on the parameters of the model that you're using. In this case, we're using a neural network, and okay, the parameters are fixed. They are, the ones that they are trained, they are fixed, but depending on the way it was trained, the accuracy, etc., you will have associated uncertainty. So the probability of the parameters given the observations is not in principle a delta, but you have some uncertainty associated to the parameter estimation itself. No? So in a way, you have to account for these two sources of uncertainty, but most of the times you don't have a well-calibrated uncertainty or data uncertainty, right? So most of the times what you see in the papers is just the model uncertainty in best of the cases, or just a naive estimation by Monte Carlo runs of the model, right? So you are only accounting for one piece of the uncertainty. Of the total uncertainty, I think it is a more complete, a more realistic view of the total, let's say, insecurity or uncertainty that you are having when providing this sort of products. In this case, we were, for example, we were having this assumption of independence between both the epistemic and the model uncertainty. I think this is reasonable in a way because the data uncertainty, let's say, is characterized by a model, by a different model, this high star FM. And then the other one that passes, of course, this uncertainty passes through the neural network, but in principle, what you're propagating and you are computing through the Jacobian of the neural network is the reflectances uncertainties, right? So you have an error bar for every single spectral channel. For when it comes to the model uncertainty, we were using this method called MC dropout, and since it is just applied to the already trained neural network, it is reasonable to assume that they are both independent, so you can sum them up, right? So yeah, but there are many ways to estimate this both epistemic and model uncertainties. In this case, we adopted this one of MC dropout, but there are others, and there are probably others more robust when you have bigger networks or you know, or lower data sets, or or
okay,
sets of not that big data sets, right?
Thank you. No question. I don't see any hand raised. Maybe a last one from me. So you presented several applications of the Gaussian process. Can you quickly summarize the advantages of Gaussian process compared to alternative machine learning techniques? It seems that you like it a lot. So can you explain briefly, what are the main advantages you found in your applications?
Yes. Well, first of all, I don't know if you're familiar with what a Gaussian process is, but this is quite old stuff from statistics and actually in the spatial statistics in the 19th century, essentially. So basically, a Gaussian process is a stochastic proof, and because of that, it is basically a collection, right? A collection of random variables, and all of them, they have a normal distribution. So that's one thing that one has to have clear. So they are collectively Gaussian. So you can, in principle, do good, and I mean, you have a very solid Bayesian framework under these models. The main advantages, answering your question, is that basically they can provide not only predictions, but well estimated uncertainties, right? So point-wise uncertainties. They can also have some mathematical tractability properties. For example, you can compute explicitly the equations for propagating uncertainties. And you can, of course, compute the derivative of a Gaussian process, which is, by the way, a Gaussian process itself. So you can analyze, or you can derive the sensitivity analysis of a Gaussian process in closed form. So you have an explicit formula to derive.
Okay, I see. Okay.
So there are many, you know, both theoretical, but also very practical advantages. Okay. On the downside, I would say that they struggle with a lot of data, because in the end, you have to invert a matrix of number of examples times number of examples. So that's very computationally demanding. But there are ways. Now there are implementations that you can use for running Gaussian processes with millions of data points. So it should be, I think, in my modest opinion, it should be one of the methods in your toolbox when you are trying regression problems. Yeah.
Thank you. So the very last question I see raised from Beiji Zhang.
I have a very general and maybe stupid question. So for the physical models, there are a lot of parameters in there, right? For example, in the Params model, So when we're using the hybrid model, so how to determine the parameter that can be estimated using the machine learning approaches?
No, it is a crucial question, actually. A very interesting one. In hybrid models, essentially, you want to combine these non-parametric models encapsulated, let's say, for example, in a neural network. Yeah. And then you have another physical piece, right? That it is, as you said, you correctly said, there it is parameterized, but okay, the functional form, maybe we can agree on it, but the parameters are quite uncertain. There is a lot of, hand waving on fixing these parameters. It is not really clear. No? Yeah. And one of the advantages here is to blend them and to estimate both sets of parameters from data. For example, you want to estimate ET, and you have your Feynman-Monteith equation, and you want to force, let's say, conservation of energy. So you would combine the neural network with your physical model that will give rise to an ET estimate. Now, what we can do with neural networks is to compute and to update all the weights, now both weights, both sets of weights, end to end. So from observational data, you can estimate the parameter of interest and learn all the weights at the same time, weights of the network and weights or parameters of the equation. And that's one of the main advantages. You are, let's say, maybe it sounds too bold, right? But you're kind of discovering these parameters or these equations from data, okay?
Okay, so not only a single parameter,
no,
a set of parameters, okay.
Yes.
Yeah, clear. Thank you.
Welcome.